Starting. Nice. Okay. Well, hello everyone. Thanks for joining us for the Excel Matlab tutorial. And this is the Excel side of things. We'll be doing Matlab tomorrow. And a lot of the focus on this won't be to, I guess, make you do anything super crazy with either of the two, but we're going to try to start from a zero understanding basis and then build you up from the basics so that you can at least start doing some interesting things relating to materials work. Like you see in Matlab's 3FO3 high temperature materials, you have to do some process modeling involving some mass and heat balances. And I'll be showing some really useful ways to do that in Excel, and Sarah will be kind of doing the mirror of that on Matlab. So without further ado, I'll get started. So the first things about Excel, I'm just going to kind of assume you've never really used it, but I definitely would. I guess the people that this is geared to for 3FO3, you would have taken the ChemEng fluid dynamics course and you would have done that. But anyways, we'll get started. So if you don't know what Excel is, it's basically just a very nice way to organize data and do some analysis on it with built-in functions that you might see up here on this upper tab. But basically each cell, it can hold values ranging from words like strings like metal students, or you can have it hold some values like 5, 6. And if it's a value, then you can do interesting things with those. So right now you just have 5 and 6 here, but let's say I want to do a sensitivity on the 5. So let's say I wanted to increase the 5 incrementally downwards, so I could just put an equal sign. And whenever you click into a cell, press equal, that'll start a formula. And when you're in this mode, if you start clicking on other cells, it'll actually highlight them and start a reference. So right now I'm referencing 013, but right now I want to reference the 5. So I'll go back in here. I'll reference this J13 or J12. I'm just going to do a simple addition like so, and then I can drag that along. And then let's say I wanted to do another interesting function with this row, like 5 times I don't know, 5, then you'll get a very straightforward function of a 5x function like that. And if you wanted to visualize this data, very straightforward, you can just highlight all of it, go to, I think it's just insert, recommended charts. Yep, so you can make charts of whatever data that you're doing. And this part of Excel is probably familiar to almost everyone that this was going to be viewing this later after the fact. But anyways, we're going to start getting more, we're going to do some more interesting Excel things that are going to be kind of useful for when you're doing some process modeling. So the very first thing that I feel like a lot of people don't understand is, let's say that I wanted to do a lookup table. So for example, whenever you're doing enthalpy calculations or even mass balance calculations, a lot of times you're going to have to reference a table for things. For example, in this case, I want to know the Al2O3 aluminum oxide. I want to know the enthalpy of formation, and I want to know the molecular weight, and I want to use it for a formula, for example. And something like that is going to be really useful when you have, right now I have a very small table, so it's very easy to read it. But in the case where you have literally hundreds or thousands of lines of stuff, it's going to be really annoying to kind of look through manually and find what you're looking for. So that's where I'm going to introduce two interesting functions that kind of does this for us. So the first one, which is going to be match. So I'm going to hit equals, type in match. And then how functions work in Excel, they have a lot of predefined ones like I showed you before. With match, you can type it out and then it'll try to find what you're looking for. You can also find sum, which is very useful. Like you can just sum a row like that or a column, and it'll give you the final output there. But in this case, we're looking at match. So I'm going to type MA. I'm going to press tab in order to complete it. And now this is Excel syntax for how they use their functions. So the very first thing is we're going to want a lookup value. So in this case, let's just say I'm interested in barium oxide. So I hit that. And then it's going to ask, okay, give me an array. I can select the entire column with all of my compounds of interest, and then hit comma. And then my final parameter is what type of match. And then you'll see that if I hit comma here, it'll give me some suggestions. Now, I know that I want to find the exact, so I'm going to press 0 in order to give me that exact match. Hit that, and 2. So what this function does is that it looks for your lookup value, in this case, barium oxide, in a lookup array. In this case, it is from Al2O3 all the way to methane, and it gives you the actual index for where it finds your lookup value. So in this case, I wanted to look for barium oxide. It is the second value in this column. So that's why when I hit enter, this function gives me 2. But then let's say if I wanted to look up, I don't know, Al2O3, I can just type in Al2O3 in quotations to recognize that this is a string. Okay, maybe I can't do that. Al2O3. Yeah, okay, maybe not. That's okay. But then I'll just do the cell reference for Al2O3, B5, and it gives me 1. And CH4, if I wanted to look for that, it should theoretically give me 3. Pretty straightforward with that one. Any questions so far? Or I guess if anyone has any questions, feel free to just unmute your mic or just type in the chat somewhere. I'll have the chat open for myself, so feel free to do so if you want any clarifications. That's the first important function we're going to have match. But then now the next important function we're going to have is called index. And index is going to be kind of like the mirror version of match, and you'll kind of know what I mean after that. So let's say I want to highlight an array. So I'm just going to highlight this one-dimensional array like so. So it's just the column here. And then what it'll actually do is it'll ask you to provide a row number. In this case, I can just show that in this array, this is row 1, this is row 2, and this is row 3. So what this function essentially does is it will let you reference something in an array, given that you know the index at which it appears. So in this case, if I'm looking for barium oxide, I can just press 2 because it's the second row in here. And then since there's no columns in this, because it's only one column, I don't need to put another one. So if I hit that, there you go. Then it'll return for me barium oxide. So you see that these two functions can come into play where when you start getting into some more complex problems, like for example here, let's say someone wants to automate this and say, I want to have a compound of interest up here, like Al2O3 or BAO, that I can just type in here. I want to have a characteristic of interest, whether it be DHF, which is the enthalpy of formation of a compound, or the molecular weight in grams per mole. So just for example here, if I put Al2O3, I want to know the enthalpy of formation, like so, then how do I write a function that looks through this table and returns me these? So relatively straightforward. Before we start doing that, I can show off first. So let's say we want to use the index function. And I showed before you can use the index function for a one-dimensional array, but you can actually use it for a two-dimensional array, such as this, because we're looking for Al2O3 as well as the DHF, the enthalpy of formation. So that's that. It'll ask us for a row number. And just looking at this manually, we can look through and say, this is row 1, this is row 2, this is row 3. That's where Al2O3 lives, so I'm going to put 3. It'll also ask you for a column number, and you'll see that this is column 1, column 2, column 3. We're looking for enthalpy of formation, so that's column 2. Click that. And theoretically, that should give us negative 1.6 million, and it does. So this is kind of the main basis of what we're trying to do in here, except the main issue being that you saw here that I had to manually look for 3, which is Al2O3, manually look for 2, which is the enthalpy of formation. We want our Excel to do that automatically. So there's a few ways to do this, but the first is going to be using something that I showed earlier. And you might think, oh, well, this is just the index of something that we're looking for. And what did we know that could find that? The max function or match function. So pretty straightforward. If I'm looking for Al2O3, I just have to click or type in match. My lookup value is Al2O3, which is the cell I4 or I3, which is why it's here. My lookup array, I'm just going to have it be the column array because that's what I'm looking for. And then I want to find an exact match. And you'll know that this will give us 3. And that's exactly what we want for this first section as the row number. So what I can do is I can just copy this little bit of code. Actually, hold on. I don't want to copy that equal sign, but I can copy this, just the max or match, insert that here, and there you go. Now it'll look for any compound of interest that I'm looking for. So let's say I want to change this. Now I want to look for BAO. There you go. It'll change that, and you'll see this also changed to 4. And if I want to look for CH4, there you go. It also updates to find our new enthalpy of formation. So that's great. That's only one half of the equation. The next half is the characteristic of interest. In this case, either enthalpy of formation or molecular weights. Right now, we're looking at DHF, enthalpy of formation, but we can do the exact same thing I showed earlier, which is use the match function, look through this array, and then hit comma, lookup array. Oh, sorry, the first thing is lookup value. That is wrong. So lookup value is our characteristic of information. Our lookup array is going to be this I guess, what do you call it? Row header along different columns. And then the match type is going to be exact. Very nice. And then theoretically, that should work for anything I want now. So let's say I want to know the molecular weight of barium oxide, and then here I can put the molecular weight. So let's put MW, or yeah, that's how that works, MW. There you go, 153.33. So this is essentially how to set up a lookup table. Very nice. How is everyone faring so far? Any questions? Nothing in the chat? Okay, so relatively straightforward stuff. Very nice. So I'm going to show a little bit more of some advanced Excel debugging, as although this looks very basic now, reality is that in the future, you're going to have to use formulas like these across entire lookup tables for, let's say, if you want to do an enthalpy calculation table. So maybe what you might even have is, let's say this is our index and match, but let's say we have multiple compounds of or multiple scenarios of interest like this. So this is only the scenario of interest of 1, 2, 3, 4, 5. And then let's say I have different values here. Like I want to fill in a table that looks for AL203. I want to find the delta H of formation there. Let's say I want the CH4, the methane. I also want to find the molecular weight of this. Is there an easy way that I can just drag this formula across? The answer is yes, but it's not as simple as just dragging things across, because in Excel, as I showed before, if we type in a formula, like for example, this one, if I want to sum these two cells, which I guess I'll add some dummy data now, we can simply drag this down, and then the cell reference will follow the drag direction. So you see that this originally has these two cells summing. When I drag it down, it'll have these two. I can drag it to the left, and then it'll have the same effect. Now it's these two cells summing, and so on, so on. That's a problem when we have index and match functions, because the main reason is we want these two cells, I3 and I4, to move as we drag to the right, because we want those to update and look for J3, J4, K3, K4. But our lookup table, so B3, D7, so that's this blue highlighted area right here, we don't want that to move, because that'll screw up our matching indexes. Like you see here, you get NA errors. So there's a very easy way to fix that. We can put in these dollar signs around the letters of the arrays that we don't want to move, like so. So we want to put it around that one. We also want to put it around this purple one, which is the column array featuring our compound names. And we also want to put it around these ones featuring our characteristics of interest, like DHF and MW. So now when I do that, I can drag this along. And there you go. It still looks for what I need. Al203, I can find the delta H of formation. CH4, methane, I can find its molecular weight. So that's some very nice ways to do that. Some other additional interesting information is, you'll notice that I put $2 signs around each letter. And there's actually a reason for that, is because if you put one around it, so for example, I just want to do sum of this plus, or sorry, let's do this plus this. And then I just put a dollar sign, a vertical dollar, or sorry, a dollar sign to the left of this J reference. Then if I were to drag this formula to the right, okay, maybe I shouldn't do that, but if I were to drag this formula down, then something interesting that you'll notice, actually, maybe I should put it on the other side. So something interesting you'll notice that if I put it on this side is that when I drag it down, you'll see that the J reference of J12 does not change. However, the K1 does change, and I didn't put anything around that. So basically what that means is that if you put the dollar sign to the right of your letter, it means that your formula will be horizontally sensitive, meaning that right now it is horizontally sensitive but vertically insensitive, so that when I drag this down vertically, it is insensitive to the change, so it will not move. And this is going to be really useful for some other interesting things when you start getting into really big lookup tables that you need to fill in. But at any rate, I think that's kind of the main point of things. Don't see any questions, so I'm just going to show off one more function that has been useful for me. And as you've all done math by now, hopefully, you would know what a dot product is. And if you don't, that's okay. So a dot product, if you take two arrays, it will simply do the product of each corresponding array element and then sum them. So like this, it's if I did array 1 times array 2 for these values, I do all of these products, and I do the sum product of these two arrays. And it gives the same as if I just did the sum of these values. So just known as the dot product, it's called sum product. It's something that I found very useful in my co-op, especially when I had to do some extra modeling. And it speeds stuff up as well if you know how to use it. But at any rate, that's kind of the main thing. So I'm going to show off another few little tips and tricks with Excel. So maybe I'll start off with, I guess, debugging. So if something doesn't work in Python or whatever programming language, there's a very easy way to tell what is referencing what. However, in Excel, as you can see, everything is quite visual. There's no code terminal for me to look through. So what I need to do is I can go to formulas and I can go click on this formula right here. And if I want to ask what is using this formula or what values are this using, so I can hit this trace precedence, and it'll actually directly show me which cells are being used to make this formula happen. And this is extremely useful when you start getting more complicated Excels, like gigantic sheets, which you will have to do when you're in 3FO3 as well as co-ops. And there's another interesting one where instead of trace precedence, you can trace dependence, which will tell you what cells are it or what other cells are using this as its dependent. So if I hit, right now I just did a simple sum of these two values. If I want to know when I'm debugging something, where is this cell being used? Easy, trace dependence, and there you go. Because I made this cell depend on these two. That's why if I try to trace the dependence of this, it'll draw an arrow to that. Okay, so I think that's probably one of the main interesting or useful things. There's also some very basic formatting things that maybe would be quite useful and be really quick for me to cover. So the first thing, what I like to do when I format my tables like this, I will like to first make an all borders, like so. I would like to do then a thick border, outside borders. I also like to isolate out the header and row column names. So I'll do that and that. And then there you go. That makes this a little bit easy for me personally to read, as now I can have those. Okay. And yeah, so I think that's the main things in terms of that I wanted to cover, getting used to Excel and I guess its basic functionalities. Does anyone have any questions or anything for me to bring up? Okay. If not, sounds good. We'll move forward. So the next bit of this is going to be very geared towards the 3FO3 project, as well as the co-op that I've been doing so far at Hatch Engineering in Mississauga as a pyrometallurgy process engineering intern. And as you'll see, I've created a little process diagram here. So if you don't know what this is a direct reduced iron furnace, given its inputs of iron ore, giving, you're going to give iron ore into the shaft furnace. It's going to perform a reduction. So this iron ore is going to be iron oxide, Fe2O3. After it is after it is reduced in here, it will come out as hot DRI, which will be assumed to have pure metallic iron. And the reducing agent is going to be hydrogen, which is going to come from an electrolyzer, which has a water input. And if you're not familiar with electrolyzing, it is essentially this reaction here where you give water, apply electrical current, and then it will produce hydrogen gas as well as oxygen gas. So right now we're only interested in the hydrogen gas that comes out of this. Now, the reaction that we're going to be looking at, as when you do 3FO3, you're going to have to look at a lot of reactions. We're going to look at this bottom one here, Fe2O3 to metallic Fe. And the really important thing that we're going to do here is we're going to know that Fe2O3, 1 mole of Fe2O3 will require 3 moles of hydrogen, and that will consequently produce 2 moles of iron at the end. Okay, so I'm going to try to keep this as simple as possible. We're assuming this iron ore input is almost entirely all Fe2O3. This electrolyzer will give us some pure hydrogen. The reactions will go fully through. There will be no bottlenecks, which in real life practicality, there will be some thermodynamic considerations, especially regarding equilibria of hydrogen gas with, I guess, water vapor. But we're not going to consider it just because it's a little bit complex. And, this is going to be as simple as possible just to get the functionalities of Excel. So in order to do all of that, I have set up this model input parameters, which simply gives us the option to give us a iron ore grade, which will tell us how much it costs, as well as how much we're giving in, as well as some composition of Fe2O3 and fluxes. Currently, don't worry about the fluxes side of things. I just put that there because realistically, your iron ore is not pure Fe2O3 or iron oxide, and it'll be useful for some later comparisons. So another aspect of Excel that I find is very, very useful is something known as named cells. So for example, right now, you'll see that I have this lookup table where I have FeOH and everything. I have its molar mass, or the consequent molar masses as well here. And now what I could do, just having this here, like, oh, if I wanted to know the molar mass of Fe, I could just visually look at this and see, oh, it's 55.845. But that becomes a problem when you have literally hundreds of these to look up, and it takes time to do that. But whereas we have Excel, we're going to automate everything. So the first thing that we're going to do is, after you create these, all you have to do in order to make this a named cell is you're going to click on this cell, go to the top left, and you're going to type in your name. You'll see that here I already typed in Fe because I've already named it. So if you look at here, I've named this as O for oxygen, H for hydrogen, Fe2O3 for, well, Fe iron oxide. So if I what the name cells do is that if I hit equals, and if I want to know the molar mass of iron, Fe, all I have to do is type in Fe. And you'll see here, I already have Fe. So if I click that, hopefully it doesn't crap out on me. Oh, okay. So right now this is formatted as percent. I want general. So there you go, 55.845. I want to know the molar mass of Fe2O3. Easy enough. Not that. I think this is happening because I ported this over from another workbook. But anyways, yeah, 159. And I also have a really important one, which is the Fe fraction, which is essentially the amount of Fe in Fe2O3 divided by the total amount molar weight. So it's just 2 Fes divided by the molar mass of Fe2O3, which gives us 0.699, which, if I convert that to a percentage, makes sense. 70% of the mass in Fe in iron oxide will be pure iron. So the goal of this little bit of this tutorial is going to be showing how you can connect this mass input in order to provide the relationships, the mass relationships in doing this reaction, where our input is going to be Fe2O3 iron oxide. We're going to have it perform a full reduction using hydrogen. And we want to know how much iron oxide does it, or iron ore does it take to produce 1 kilogram of hot DRI, which is going to be assumed to be pure iron. So in order to do that, I've set up this mass table, which is pretty straightforward. In the column labels, I have the processes and the lines between them. So number 1 is iron ore to the DRI shaft furnace, and that's just going to be our iron oxide in here. So that's that. I can do that quite easily. I'm going to hit equals. I'm just going to equal that to this feed rate here, this kilograms. But since I want this to be the Fe2O3 as named by this description, I'm going to multiply that by the amount of Fe2O3, which is 80%, which will give us 1,400 kilograms. All good so far. Number 2 is going to be the water to the electrolyzer. And then number 3 is going to be the electrolyzer to the DRI shaft furnace, and this is going to be hydrogen. However, we are unable to fill these in right now because we don't know exactly how much we're going to need. And that's something that the model is going to calculate. So what we can do, though, right now, we know that iron oxide, Fe2O3, is going into the furnace, and we know that it will be fully reduced. And how do we find out how much fully reduced metallic iron we'll have? Well, pretty straightforward. All we have to do is perform this reaction using its molar ratios. For example, 1 mole of Fe2O3 will produce 2 moles of Fe. And then once we know that, we can just do the math in this molar section and then convert it back to kilograms. And that'll be our how much iron we're going to make. And that might sound a little confusing, but I think it's easier if I just showed to do it. So the first thing we want to know is how many moles of Fe2O3 do we have in here? So given that I showed we already did this kind of name table, this would be super easy. Now, all we have to do is divide this. So we're going to hit equals the mass of Fe2O3 divided by the molar mass of Fe2O3 that we've already defined. And that'll give us 9,000 moles, because keep in mind, I'm doing kilograms here. So this will have to be 1,000 moles as well. So 8.9, that makes sense. Now, here comes the easy part. Now we can exactly define how much hydrogen we're going to need, how much water we're going to need, as well as how much iron is made at the end using this equation. So let's just start really easy. How much iron is made? It's simply going to be 2 times amount as the 2 times the molar amount of our iron oxide. So I'm going to go to stream 4, which is the iron out, go to metallic Fe, equals simply this value times 2. If that doesn't make sense, feel free to message in the chat and I'll explain further. But regardless, it's quite simple. The next thing is going to be hydrogen, because I you don't want to know the output water. We want to know how much water is input to create that hydrogen. So the first thing now, we know it takes 3 hydrogen moles in order to react with 1 mole of Fe2O3. So with that very similar process, we're going to go to stream 3 because this is our hydrogen stream, go down to our hydrogen. We're going to simply equal, and you see here, I wrote it down, 3 moles of hydrogen per mole of Fe2O3 to reduce the iron. So I just have to hit this times 3. There you go, 26 moles. And then if we want to know how much water, very straightforward, I have this reaction here. 1 mole of hydrogen reacts or is made from 1 mole of water. So then the moles of water here, water to electrolyzer, is simply also going to equal to this value. And that's it. We've essentially figured out exactly how much iron, hydrogen, and water we're going to need in this process. However, typically we don't want to report these to a client or in your project as moles. They're going to want a more concrete thing that they need to know that they can compare to their, for example, how much hydrogen or how much water they need to use, or how much electricity they need to use on the basis of hydrogen per kilograms. So in order to do that, it's pretty straightforward. We just have to convert these back to our kilograms. So the first thing I'm going to do is make this metallic one. So I'm just going to equal the number of moles times, or 1,000 moles, times the value of Fe, which we know is 55.84, and it's already going to be self-referenced here if I type in Fe. Very nice, very easy. There you go, 1,000 kilograms of finished Fe. And I made it like this because, or the value, it just makes it to 1,000 because I ran the scenario earlier, but regardless, we're going to do the rest for the rest. We're going to do the same for the rest. We have hydrogen, so I'm going to multiply this by our amount of moles times the molar mass of hydrogen, which I've just named H. Yes, this makes sense because H is just 1 point, it's almost 1, so that's expected. And then next we want water. Straightforward again, multiply this by our amount of water, H2O. There you go, 400 kilograms of water makes 27 kilograms of hydrogen, which therefore reduces 1,400 kilograms of iron ore pellets into 1,000 pounds or kilograms of DRI, direct reduced iron. And now all it's left to do is to connect this all to the model backend. So now I have the model output summary. I'm going to put in the amount of hot DRI made into this 1,000 value. I'm going to put in the amount of water made in water required in kilograms into that. I'm going to put in the hydrogen required into this. And there you go. You've effectively modeled, albeit a very simple case, but still nonetheless modeled a hydrogen-based iron reduction plant. And now this is going to be really useful because in your project, I mean, this is basically what you're doing from what I understand. I haven't taken the course, but I've heard lots about it. This is effectively what you need to know. And for me as a process engineering intern, or if I was a process engineer, this would be really good because then I could show this to the client and say, in order to, if you have an iron ore grade of 80% Fe2O3, it will take you approximately because this is a very rule of thumb model, approximately 1,400 kilograms of iron. Why is this 14? Oh yeah, because it's 1,400. So it's that. It'll take you 1,700 of iron ore in order to make your 1,000. Now, the reason why this is really, really useful as an Excel model, like, oh, great, I could have just calculated this, with my calculator using some basic ratios. But now let's say you want to run a bunch of cases and you want to say, oh, but what if, and also another thing we should add is price. So let's say price, we do just simple this times your tons of ore, which is just going to be this divided by 1,000 because it's kilograms, turn it to tons, metric tons. So now we have $178 per ton of hot DRI. So now what if the client says, oh, can I get away with having a cheaper grade of ore with lower Fe2O3? And, if you didn't use Excel, you would have to do all of that calculation by hand all over again. But because we did, we can just, write the scenario. So let's do $60. And then let's make this decrease by a factor of 60 or the 20%. And you see that, there you go. Oh, actually, no, so not yet. So right now we have to renormalize this to 1,000. And in order to do that, what I'm going to do is I'm going to go to data. Oh, I don't have solver here, do I? Okay, so we're going to use something called solver, but I don't have it right now. And I'll show you how to add it to your Excel if you haven't. So go to file, go to options, go to add-ins, if it loads. Okay, and then I'm going to go to solver add-in. I think I just hit go. Give me all of these. Thank you. Is that going to restart my use Excel. Nope. Okay, nice, we're good. So now you'll notice that this just appeared here, which gives us this solver thing. And what this will do is it'll help us renormalize this back to 1,000 kilograms, because right now you'll notice that it's at 750. We want to do the comparison for 1,000. Obviously, I could just like manually type this in until I get 1,000. See, I'm at 800 now, and maybe, I don't know, 2,300. That's closer, but if you want to do it automatically, we want to set our objective. We want this objective to be of a value of 1,000. We want to change this cell here because this value is fed into this model, which does the calculation and relays it to this hot DRI value. And we're not going to add a constraint, so I'm going to delete that. And yeah, I think that's it. So I hit solve, and then it'll show here, solver has found a solution. There we go. So now, after decreasing the price of the ore, but having a poopier ore with less Fe2O3, it costs us a lot more iron ore to make 1,000 hot DRI. And you'll notice that the price, I think it decreased because there was originally $1,700 per ton. And you'll see that, wow, by using a worse ore, you can actually save some money, even though it takes a lot more feed material in order to produce the same amount of output. Now, that would be okay, but this model, again, is very rule of thumb. There's a lot of things to consider, like, for example, as we are material students, we'll know that if you have a cheaper grade of ore, it'll have some other trace elements, like, for example, sulfur content, which is something that is very bad in steel. It is a very undesirable constituent to have in it, and it causes problems due to its, I think it makes it brittle or something, but basically it'll cost a lot more money to remove sulfur in the end. So you would have to reflect that in this price calculator. However, this is a very rule of thumb model, but the point being, if we did have additional parameters to include for the amount of fluxes, like another penalty, like we said, price, but then we'll increase the price for however much fluxes you have by a factor of, like, I don't know, like 20. Then that will play in when you put in the solver. And that's basically, I guess, kind of the main thing, where now we were able to build a rule of thumb model that does a whole mass balance based on chemical equations of our process. And in doing so, we're able to use solver in order to normalize all of our data for comparison, so that by normalize, I mean all of our price comparisons are done by a per ton or per 1,000 kilograms of hot DRI basis. So that's pretty good. That's more or less the main objective of today that I wanted to run through. Sarah, is there anything immediately that I might also want to run through before we jump off?
Do you want to show the dependency tracker?
Yeah, sure. Like for this, or like what?
For anything, to basically, so like if you're looking at, let's say your group members Excel, and you're confused as heck what things are made up of and how they kind of made the formulas, there's a way you can track them.
Yeah, exactly. So let's say I wasn't responsible for the Excel, my partner was, and I want to check where they went wrong. Like, let's say this number looks like a million or something. Well, I can hit trace precedence. It'll show me that this is equal to this value. Makes sense. I can hit trace precedence again, and I can see that they converted the molar value of Fe metallic using the molar mass. Okay, makes sense so far. It's getting cluttered, so I'm going to hit remove arrows. I'm going to go here, trace precedence again. Okay, well, I can see that now this is simply the molar relationship between metallic iron reduced by Fe2O3, which is times 2. Okay, sounds good. Go back to here, trace precedence again, and I see that, oh, okay, so this is just the Fe2O3 divided by this molar weight, which makes sense, converting kilograms to kilomoles. And then last but not least, I can check this, trace precedence, and I can see here, oh, okay, so they just took the feed material, multiplied it by its mass weight, or mass percent of Fe2O3, and that gives them the kilograms to Fe2O3. And there you go. I've effectively fully traced how they got this number. And that's going to be something that's going to be really useful, because Excel, although it is more visual, sometimes it can get very overwhelming when your sheet, because right now everything is like in this frame. But when I work on my own models that I work at Hatch, like I often go into like the BF/BQ range. So then in order to trace stuff, I have to like do this a lot. So something really useful that you might not know is if I hit equals here, equals this, go back. I want to look at the dependence of this. I think I can double click this arrow. Yeah, if you double click the arrow, it'll directly zoom you over to where you're looking for. Let's say I have another value in another sheet, because typically your lookup tables will be in another tab here. Let's just name, I don't know, I'm just going to put a random number in here. And then let's just say I'm going to make a cell here, reference that number like so. And let's say, you want to find out, where did I get this thing from? Trace precedence. Oh, look at that. It's not on this sheet. I can double click this and it'll show you, okay, so the file it's in is called DRI model Excel tutorial, which makes sense. That's my file. Sheet 5, E28. I don't want to close this and look through sheet 5. I can just double click this. It'll take me there. So that's another really useful shortcut that I find has helped me personally a very lot. And yeah, does that about cover that, Sarah?
Yeah, that's good. The only other thing I find sometimes can be helpful is if you're working on these really large sheets that are often, quite entangled. Do you know how to open up the thing where it basically has like a window on the top and a window on the bottom, but looking at the same kind of range?
You mean like having two of these things open? I think your mic's not picking you up because I can hear you upstairs.
Basically, just you know how you can do it in VS Code where you can look at the same window, but in kind of one frame at the top, one frame at the bottom.
Yeah, I know you can do that. I haven't done it recently. I think it's one of these things. It's not that.
I know the freeze panes thing is also useful.
Yeah, freeze panes is useful for if you have a really long lookup table, I don't know, if you had this is your index, then you have values all in here. Let's say this is your labels, like DRI, steel, molten iron, I don't know, stuff like that. If you wanted to look down on this table, but you want to keep this in here, you can go hit the kind of boundary between these two, like this column and this row, hit freeze panes. And then now it'll make sure that you always see whatever is above or to the left of that pane. So you see now I'm in row 116, but I can still see DRI, steel, molten iron in row 18. But yeah, the other thing, Sarah, I don't really use it that much, but I mean, you can probably Google it. It's not, yeah.
I think it might be the view side-by-side button right up top, but anyway, nonetheless. Yeah, there you
go. So now I can have, yeah, preferably I'd want it left, right, but I mean, you can change that probably.
Yeah.
But yeah, I tend to not do that because you can see this looks really messy when you have two UIs. If you have a really big monitor, then it's more useful, but I find it's not super great. But anyways, so that's that. Maybe I'll show one quick thing where here, this is another Excel file that I made where instead of having only one OR grade input here, I put in a blend. So you have OR grade 1, 2, 3 with varying prices, the most expensive having the highest FE203 content. And what I did here was I basically ran the solver in order to try to compare and say, what is the best scenario and best feed rate between these that I can get the cheapest OR for my ton of hot DRI? I'm not really going to show how to run that solver because it's pretty straightforward and it's kind of similar to what we did. Actually, I might as well. So I'll hit solver. Now this is going to be different. I don't want my objective cell to be the 1000 anymore because I'm not maximizing or minimizing that. I can set that something else. But what I will do, I want to minimize my price because I want to optimize, optimize stonks for my client. I want to change all three of these feed rates. This is basically letting the solver, it's going to not randomly, but it'll systematically move these things around, change these values until this price becomes minimum. And in order to make sure I have 1 ton of hot DRI, I can simply add a constraint, which will make sure that this results in 1000. So I just have to hit that, hit equals, constraint 1000, that's 10,000, 1000, there you go. And then that'll effectively do what we need. Now, this case, the reason why I didn't want to show it too much is because it effectively boils down to which OR grade provides the best bang for your buck. By bang for your buck, I mean literally the dollars, or maybe not dollars, but the amount of FE203 divided by your dollars. And it comes down to which one has the highest value, and it will choose 100% of that. But this kind of solver is more interesting when you have other factors. Like, for example, I mentioned the factor involving sulfur. If you have a lot of fluxes, perhaps sulfur is going to be one of them, and that's really problematic. That will introduce a exponentially increasing cost versus not including it. And since right now all of this calculation is very linear, it's not going to reflect that. But if you did, then the solver might, it might actually rejig these and try to find a optimal solution where you use a little bit of one, a little bit of two, a little bit of three. Now, another interesting thing that we could do is if I open up solver, I could add another constraint where this one, because I know this is going to go to 100. Let's say, you're a supplier, you're like, I simply do not have enough of ore grade 1. So let's say I can only max this out at 50% feed, or let's say 45, like so. And then the solver will try to use the next best grade in order to compensate. So when I hit solve, did it do it? It did not. Okay, let me go back. I think I realized what I did. Yeah, so this is wrong. This needs to be, this cell, which is D5, needs to be less than or equal to, oh, sorry, this is 0.45 because it's working in percentages. That makes sense. Okay, let's try that again. There you go. So now I'm at 45%. And then the solver determines that this ore grade is the next best for your money, which I show here it is. So it plops everything in there. It automatically does all of the FE calculations, which otherwise you do by hand, and gives us our final price. So I think I've talked enough. I've shown, I think, quite briefly the extent of Excel that you would need in order to kind of work with 3FO3. Maybe I'll do additional tutorials in the future. We definitely will do additional tutorials later involving this developer tab, where we can record macros as well as actually, start writing code that executes our Excel spreadsheets. And that's going to be really useful for 3F when you need to do optimizations multiple times over. And I think Jeremy, who is also here, is going to be running that tutorial at some point in the next few months. But yeah, otherwise, I think that's more or less everything I wanted to cover. Sarah, is there anything else I kind of missed, or you think that's probably good for tonight?
No, that's good. Does anybody have any questions or anything they struggle with and they want any help out? Otherwise, tomorrow we're going to be going through the Matlab side of things because basically Excel is really great in an intro side because it's very visual, like Irene said. But then once you start doing some coursework where you're running multiple optimization cases and you're not necessarily like wanting to have to learn VBA, that's where, we're going to run through the basics of Matlab and then go over some ways that you can basically save yourself a lot of time that Excel won't be able to unless you kind of invest really in learning VBA.
Yep, what she said. I think this project for 3F, I haven't taken it, but from what it seems, Sarah, this is kind of like the basis of what you were looking for me to cover, right? In terms of like the stream table and doing the molar calculations, or?
Yeah, no, exactly. Because now it's going to be, okay, so we can set this up. We can do a little balance, but now we're going to be given, a range of optimization that we're going to have to do, and it's going to be like a nested multiple set of loops.
Yep.
So
yep.
It gets complicated when you start using Excel in it, unless you do it manually, like some people I know did, and just
pressing a button
change
like
the number,
times.
replotted it, copied the graph, changed the number,
Yeah, pain. Yeah, Excel is very nice because everything that Sarah kind of described can be done automatically, and it's really not that hard. Jeremy did his 3FO3 project using Excel, and it was quite simple. And he learned VBA just for that, actually. But anyways, we'll probably cover the VBA side of things another day, as Excel can be a lot already, since I really like just looking at this now, how to model really any process. If you know how the thermodynamic equilibrium plays in, you can code that into here. And this is actually based on a hydrogen DRI model that I made for Hatch. This is actually very similar to what it looks like. However, it is a lot more complex. I did code in those equilibrium requirements, and I did optimize in order to look for the correct temperatures in order to meet those requirements. Took many weeks, but anyways, in terms of a first step, I think this is a good first kind of glance at how to do this kind of stuff.
Yeah, and that's really where a lot of the value comes in when translating this to Matlab, because doing all those enthalpy conditionals, if you remember, like integrate like this from 0 there's from 298 to 400, and then this from 400 to this and this, you have to make sure that, at each stage it's only using the right temperature maximum for each enthalpy. And that's really where in 3F I found.
Oh, sorry, go ahead. Sarah? Okay, I think Sarah might have disconnected or something, but
it might just be lagging.
Okay. Are you good now?
Did anything I said pass through?
Nope. Okay, that's okay. Do you want to give it one more go and then we'll finish off?
Yeah, sorry. I was just saying how when it comes to like doing enthalpy calculations, like you remember, you have to go from like 298 to 400 and 400 to 600 with this condition. I found it a lot easier to set up all those conditionals in Matlab, and that's what we're going to go through tomorrow.
Yep. And by what Sarah means about that is right here, if you look at, this isn't enthalpies, but for example, they have some thermodynamic modeling where they have like this equation in order to find the vapor pressure, and it's dependent by these coefficients. However, the coefficients change over different temperature ranges, and that's exactly what you need to be coding in when you do 3FO3. And MATLAB is very nice for doing that kind of stuff. But anyways, I think we've talked enough, Sarah. Jeremy, do you have any comments, or you're chilling?
No, I think everything that you covered was excellent.
Thank you, sir. Looking forward to learning some VBA from you. VBA will be interesting. Oh, there's some chat stuff. Yep. Anyways, so if you're interested to join the MATLAB side of things,